Hey everybody, Dr. A here, and in this video we're going to be exploring some background information on how to compute a moment about an axis. So let's go ahead and get started. So far what we have discussed and explored are moments about a point, and we've done that both in 2 dimensions and 3 dimensions. Now what we want to talk about is a moment about an axis, or possibly even multiple moments about axes. Okay, so what's the difference? Well, mathematically there's a little bit of a difference, but physically that's where we want to make sure we understand physically and conceptually what's going on. So to help us do that, let's take a look at this 3D figure we have here. So in this figure, I'm asking us to consider the force vector F that is causing a rotation about an axis called AA. So I've got this red axis here, AA, all right? And again, this is supposed to be a 3D figure. And I have this force vector hanging out somewhere over here, and it has some kind of distance defined by this position vector r away from this axis. Now what's happening is as this force acts, as I've drawn it here, it's going to cause a rotation around or about, we sometimes say about, that AA axis, okay? And that's shown here by this moment vector m sub a, all right? Now, what about this point O right here? Well, this is just kind of a help point to define the tail end of that position vector r right here, okay? So how do we piece this together, and how do we define these things? Well, as I've kind of drawn in the picture, m sub a is the moment vector about the AA axis, okay? F is the force vector causing m sub a. Now, what about r? Okay, this is clearly it's a position vector, but more specifically, what is r? Well, r is the position vector whose tail is at any point O on the AA axis and whose head is at any point on the line of action of the force F. Okay, so here's the interesting thing about this position vector r. Its tail is going to be, it can be defined as any point on this AA axis. So it could be here, it could be here, it could be here. Any point on the axis that you're trying to find the moment about, all right? And its head is going to be at any point along the line of action of the force in question. So, you know, we could draw this. We could draw R, for example, like this. You know, it could be, the tail could be up here, and, you know, R is defined right here. Or the tail could be down here, and R is defined like this, okay? So that's the cool, I'm gonna erase this or backspace it a little bit. So that's the cool thing about R. So as we're tackling these numerical problems, if we remember this little fact right here, it'll make our analysis and our computations go a little smoother and faster, okay? Now, in 2 dimensions, if this were to break down into a 2-dimensional problem, then what would it look like? Well, in 2 dimensions, it would just reduce back down to a force times a perpendicular distance away from a point. So let's go ahead and sketch that out. let's say in 2D, if I were to look down from above on top of that AA axis, what would I see? I would just see a little point like this. Okay, so again, if I have an eyeball up here and I'm looking down on this axis, that's what I'll see. And you know, I would see maybe this this force vector like this, F, and then of course, you know, I would see you know, some kind of position vector like this, R, okay? And then of course, you know, the moment that's generated, I keep clicking the wrong button here. The moment that's generated about this is going to be M sub A, but again, in 2D, this reduces down to the moment about a point because why? In 2D, A is going to be incident with point O. So this could be rethought of as MO. And then, of course, we know from before that MO is R cross F. Okay, so in 2D, if you were to look down upon an axis that's like coming out of the screen at us, then it becomes a 2D regular cross product problem like we've talked about already, okay? And then you could use scalar analysis even, okay? Now in 3D, we typically, so back on this view here, we typically use a Cartesian vector analysis. So let's talk about that, okay? So I'm going to come down here. I'm going to say in 3D, we use a Cartesian analysis, all right? Now in 3D, you're going to have some kind of defined axis, okay? And so what that's going to end up being pieced together as is going to be MA equals U sub A dotted with that R cross F, okay? Now, that R cross F here is the same R and the same F that I showed in my first 3D figure here. It's R cross F, but now I've got this three-dimensional axis that is somehow defined in 3 space, okay? And so because of that, I need to incorporate its essence into this. And I do that using the unit vector of that axis A, all right? So let's write this down. We're going to say U sub A is the unit vector that defines the AA axis, which is really, you know, whatever the axis is, your desired axis that you're trying to find the moment about, okay? Now, here's what's cool about this. You remember from the cross product is basically, you know, evaluating a 3x3 determinant, okay? And so how this pieces together is the following. You're going to have MA, and you're going to have the unit vector of A. What is the unit vector of A? Well, you'll have, you know, UAX, comma, UAY, comma, UAZ, all right? So the unit vector that defines that axis, okay? And then again, you're dotting it, you're doing a dot product with R cross F, all right? And so we already know what R cross F is, don't we? So we could say MA is, you know, UAX, comma, UAY, comma, UAZ, dotted with that determinant, okay? What is the determinant that defines the cross product of R cross F? Well, if you remember, that's I, J, K, and then we have Rx, Ry, Rz, Fx, Fy, Fz, and determinant that. Now, here's the way, what's cool about this, the way this works out, and we could do a mathematical proof. I'm not going to, but we could. When you dot this vector with this determinant, what you actually end up getting is a determinant, okay? And so what ends up happening is you end up getting MA equals determinant UAX, UAY, UAZ, RX, RY, RZ, FX, FY, FZ. Now, here's a question for you, okay? And I delayed on doing this particular formatting on purpose to see if we can piece it together ourselves, okay? When we put this determinant together in this form, these are all numbers here, right? These are all just like real valued numbers, constants in here. When you take a determinant, a 3 by 3 determinant of all numbers here, we don't have these unit vectors anymore, IJK anymore. These are all actual numbers. Whenever you find that 3 by 3 determinant, what do you end up getting? You actually get a single real number, which really means what? It really means that this MA is the magnitude of MA. So what we need to do is put magnitude notation around all of these MAs. Okay, so go back and do that in your notes if you hadn't done it along the way. You might have already known that. You might have been able to figure that out as we were going along. But this ends up being a single real number. So really, this is the magnitude of MA. It's not a Cartesian vector, okay? So then my next question becomes, what if you're in a situation or you got a problem that asks for the moment about an axis as a Cartesian vector? Well, this gets you the magnitude. So if we want MA as a Cartesian vector, here's what we do. We're going to say if we want the Cartesian vector MA, guess what we do? We say Cartesian vector MA is that magnitude that we just calculated multiplied by what? The unit vector of that axis, okay? So what we do is we take that magnitude, which we just got a single real number, which we got using the unit vector of the axis. You know, we already used it, so we already have this, and we just do a regular multiplication with that unit vector of that axis, okay? So that is it. That's it in a nutshell for a moment about an axis. And then, of course, if you have multiple of these, you would use a summation version, okay? So again, if you wanted, like, let's say you have multiple forces causing rotations about a particular axis, you would just throw in, a summation notation somewhere in here, and then you can find like a total resultant moment about an axis. All right, so that concludes this background information. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.